Hello everybody! In this clip we determine the divisor class group of a toric variety in terms of its defining lattice fan. First we recall the concept of divisors. Let X be any variety. A prime divisor on X is an irreducible closed subset Y of dimension 1 less than X. The Y divisor group of X is a free abelian group generated by all these prime divisors of X. So a Y divisor on X is a linear combination D of prime divisors Di with integral coefficients Ai. Let us look at a toric variety xt, x0 arising from a lattice fan sigma in N. Consider the primitive generators V1 up to Vr of sigma. Then each of these primitive generators defines a prime divisor, denoted by rho I, the ray generated by Vi, and by Di, the closure of the torus orbit through the limit point x rho I. This is a prime divisor. Indeed, our ray rho I is of dimension 1, so the corresponding orbit closure Di is of codimension 1 in X. Moreover, these Di are all invariant under the torus T. And if I remove the torus orbit through the base point x0 from X, what is left is exactly the union of our divisors D1 up to Dr. The divisors D1 up to Dr generate the subgroup of invariant Y divisors in the Y divisor group of X. We will associate with any non-zero rational function a divisor. For this, we first need the notion of the order of a function along a prime divisor. Consider a normal variety, a prime divisor Y in our variety X. Then, as a consequence of normality, there is an open affine subset U in X, such that the intersection of Y and U is non-empty, and the vanishing ideal of this intersection in the algebra of functions of U is generated by a single element Gy. Now the order of a non-zero rational function along Y is defined as follows. Write our function f as a quotient f1 by f2 with regular functions fi living on U. Then the order of f along Y is defined as the order of f1 minus the order of f2, both along Y, and the order of these regular functions fi on U is defined as the maximum integer such that the corresponding power of the ideal generator Gy divides our fi. At the end, this turns out to be well defined. That means it is independent on all the choices we made through this definition. Let us look at an example. The order of a monomial Ku equals z1 to the u1 up to zn to the un along the i's coordinate hyperplane di in Cn is order of Ku along di equal ui, and this ui we can also interpret as linear form u applied to the basis vector ei. This point of view shows how to proceed more generally in the case of toric varieties. Consider an affine toric variety X row defined by an array row with primitive generator V in some lattice n. Then the order of a character function Ku along D row is U applied to the primitive generator. This is seen by transferring this situation via a suitable toric isomorphism into that situation. Now, having the concept of an order, we can associate with any non-zero rational function on a normal variety its divisor. The divisor of f is the linear combination over all the prime divisors in X, and the coefficients are just the orders of f along the prime divisor y. We determine the divisor of a character function on a toric variety. So look at the toric variety arising from a lattice fan. Consider the primitive generators V1 up to VR of the fan and the associated toric prime divisors D1 up to DR. Then the order of a character function Ku on X along such Di is U applied to the primitive generator Vi. The reason for this is that we can determine this order on a suitable open affine subset, and this we did just before. So the divisor of a character function is given as divisor of Ku is U applied to primitive generator V1 times D1 up to U applied to primitive generator VR times DR. We are approaching the divisor class group. First, let us recall the definition. On a normal variety X, passing from rational functions to their divisors defines a group homomorphism from the multiplicative group of the function field to the Weil divisor group, sending a function f to its divisor. The image of this homomorphism is a subgroup of principal divisors. And the divisor class group of X is a factor group Weil divisors of X modulo principal divisors of X. Here are some thoughts about the divisor class group of a toric variety. The algebra of functions of the torus is a Laurent monomial algebra, so it is a unique factorization domain. The latter means that every Weil divisor on the torus and also on the torus orbit through x0 is a principal divisor. So that means on the toric variety X, modulo principal divisors, every divisor can be represented by a linear combination of our toric prime divisors Di. For the class group, this means that divisor class group of a toric variety is invariant Weil divisors modulo invariant principal divisors. And the invariant principal divisors turn out to be just the divisors of the character functions on the toric variety. We are ready for the final theorem. Consider the toric variety arising from a lattice fan. Then we have a commutative diagram with exact rows. Let us look at the ingredients of this diagram. We see the character group of the torus, we see the group of invariant Weil divisors of X, and we see the divisor class group of X. In the upper row, we have the dual lattice M of N. Then we have this map P star. P star is a dual of the map P going from ZR to N, sending the ith canonical basis vector to the ith primitive generator of the fan. And the projection Q from ZR to K is just the projection onto the factor group ZR modulo P star N. Now, there are some known things. We know that the characters of T are all of the form chi U, where U stands from N. From here to here, we take a character and send it to its divisor on the toric variety X. From here to here, we send every invariant divisor to its class in the divisor class group of X. From ZR to the invariant Y divisors, we have an isomorphism, sending a vector A to the sum AI di, where di are the invariant prime divisors of X. And altogether, our diagram allows us to compute this divisor class group entirely in terms of data of the defining fan of X. See you in the next clip.